Hello, everyone. My name is Spencer Bryson, and I'm pleased to present to you today at Canadian AI 2021 Bluetune, Continuous Knobs Tuning. This is a project done in collaboration between IBM, York University, and Ontario Tech University. So, what exactly is knob tuning? Well, it relates to database management systems, in particular IBM DB2. And these systems have dozens of knobs, or even hundreds, also known as configuration parameters, that effectively control how they perform and operate. Some of the knobs might include those relating to memory pools, such as sort heap size, buffer pool size. Other knobs might be pertaining to different levels of optimization for the query optimizer. Some might control concurrency and degrees of parallelism. And there's much more. And all these knobs must be properly adjusted to achieve high performance and scalability. And this is usually measured in high throughput and low latency. So effectively, we must adjust these knobs to maximize the performance that the database management system can achieve. Traditionally, databases usually rely on database administrators in order to tune the knobs. There is some auto configuration available, but it's generally limited. It usually uses heuristics and stuff like that. So in most cases, usually when there's a problem, an expert is actually required to tune the knobs. And this is actually a non-trivial problem. If you can imagine, if there's dozens or hundreds of knobs, trying to figure out the best setting for each can prove to be quite difficult, right? So it would take a lot of experience and a lot of expert knowledge to figure this out. And it can even take several days of an expert analyzing of a database and the workload to come up with a proper setting. So another thing to note too is that sure, the expert can come up with a decent configuration for the client or end user, but as these clients' workloads evolve over time, business applications might change, the queries and the underlying data might change over time, and this can lead to the configuration no longer being optimal. So this obviously would lead to poor performance until the knobs are retuned, until another expert comes to manually perform the tuning. So you can kind of get a sense now that a fully automated approach to optimally tune the knobs is desired. The goal is to relieve the burden of tuning from these experts whose time are quite precious and expertise could be used elsewhere. But we also believe that it's possible that we can find better configurations than experts, right? Like there's so many knobs, it's quite difficult for a human to figure out, right? And yeah, another thing we noted previously was that businesses and their applications aren't static. Their workloads are going to change, so the knobs must follow. You can no longer just set it and forget it. You're gonna have to be continuously improving your configuration as the underlying workload changes over time. So to highlight some challenges and use cases with this, one of the reasons why it's so difficult for human experts to tune as well is that a lot of the knobs are continuous values. They're not always discrete choices, yes or no, or a limited selection of choices. Generally, many of them are continuous. So that means that there could, in theory, be any number of choices, almost infinite number of combinations, because we're kind of dealing in a continuous space. And you can kind of see that here from the plots that I'm showing, with two particular knobs, sort heap and buffer pool size, both measured in pages. And you can see how altering them effectively impacts the overall cost of the query. One thing to also note is that these knobs can be interdependent, right? As you alter one, you might be impacting the benefit of the other. And that's kind of why we're seeing different patterns here in the plots. And it's also pretty apparent that these are two separate queries, right? And it's clear that the charts don't look identical, right? So one configuration can't necessarily fit all. So not only does this mean you're going to have to update it, but it would be nice to choose and change configurations based on, the current workload that you're processing, right? You don't just want one blanket configuration that catches everything. We're going to want to handle with different workloads. So our approach and the architecture behind it, from a very simple standpoint, it's a deep reinforcement learning solution. It uses actor-critic, so you can see within the agent in the figure, we actually have two neural networks here, one for the critic, one for the actor. If you're not familiar with how actor-critic works, the actor is responsible for deciding on the actions to take, and the critic essentially criticizes and scores those actions. And they kind of work together to improve the performance of both of them together. Like they work together to achieve this. So yeah, this is a policy-based learning method, and we use this architecture to determine the next likely best action. Another component we've been focusing on quite a bit has been the embeddings. So, if you think of a query, you think of SQL, right? How exactly does this translate into something the agent can understand? We're looking at, taking it a step further here, and instead of looking at the query itself, we can look at query execution plans. That gives us a bit more information, stuff like costs, how joins are working here. So it's a lot more descriptive representation, but it also does lead to some difficulties in finding a suitable representative for it. So we're looking into embeddings to actually use instead of the raw QEP. So in general, actor-critic is a reward-driven learning algorithm. It's reinforcement learning. So by design, the agent's behavior is driven by the reward function that we've come up with, right? So in general, the goal is to maximize the reward. That's what the agent's interested in doing. Our reward that we give the agent is based on a change in query performance. So depending how the agent tunes or produces an action to tune the knobs, we evaluate it against actual performance and reward the agent that way. So it could be something, as simple as execution time. How does the knobs impact the execution time? If it lowers the execution time, that's good, and that can be positive reward, right? If it increases execution time, that's not so good, right? And one key thing here, though, is another thing we've been considering is the optimizer cost itself. All, if not most, modern database management systems have query optimizers in them. So the SQL statement, the query that you write and that you submit to the database, is effectively rewritten or changed using, a lot of rules, heuristics, statistics, to try to improve the performance of the query behind the scenes without the user intervening. And from this, we actually can get an estimated cost because the optimizer is trying to optimize the query. It has a sense of what it estimates the cost of the query is going to be. This cost is an execution time. It's measured in time runs, but in general, the cost is a good indicator of what performance you might be able to expect. So our reward also, we do use exponential decay with the rolling cost history to kind of help steer the agent in the right direction, and to kind of almost have a short-term gauge of how much better are you doing than 3 iterations ago or 10 iterations ago. And we factor this into the final reward function using exponential decay to help guide the learning. Another thing to note is that our reward function also enforces some constraints, stuff like limit resources. So a lot of the knobs do pertain to memory. Without enforcing this, the agent gets quite smart and tries to use as much memory as it can. But we've incorporated components into our reward to at least obey by constraints and use a reasonable amount of memory, because this might be important in a cloud computing environment or somewhere where you have limited resources. So just to touch on this whole execution time versus optimizer cost, the overall goal of the agent is to minimize the execution time by finding a suitable configuration. That's kind of what's desired by the end user. We want less time to execute queries. One thing to note, though, is that trying to train a reinforcement learning algorithm on execution time itself can get prohibitively expensive as the complexity of the queries and the size of the database grows, because you're waiting for the query to be executed, right? So it's not like the learning isn't expensive itself, it's just waiting for the results from the execution time. So it can get quite lengthy. And the databases that we're kind of targeting are 100 gigabytes and larger, so you can imagine some queries do take a while. So trying to get enough iterations, enough data for the reinforcement learning agent to understand something ends up taking a long time if you base it solely on execution time. However, what we're demonstrating here is that you can use optimizer cost in lieu of execution time. It greatly speeds up training. Some early benchmarking to give you a comparison is that 20 episodes can be done on optimizer cost in 7 hours, whereas 5 episodes take 38 hours, right? So there's a massive gap in time taken here. So what we've come up with is fine-tuning the model. So as stated before, execution time takes a long time. So if we take a look at optimizer cost, we know it can be an effective measure performance for the various knob changes. However, execution time at the end of the day will always capture most of the information that we want. So the optimizer is known to sometimes have inaccurate estimates because, well, they're estimates, right? So there is probabilities of it making incorrect estimates. Some knobs aren't always fully factored into the optimizer, so it's hard to learn solely on that. So with this knowledge, knowing that, it's kind of desirable to use the concept of transfer learning. So what if, we just first trained up a model on minimizing optimizer cost, and then reusing that model, we fine-tune it and improve it by training on minimizing execution time instead. And you can kind of probably see where this is going. So some early results is that the first model, where we only train on cost, it's a lot faster than the execution time. It takes less than 4 hours for 10 episodes, so we weren't doing too much work here. And you can see on the left-hand side of the chart, episode versus optimizer cost. You can kind of get a sense that, yeah, okay, the agent is able to figure out how to minimize the cost from the optimizer by finding appropriate configurations over time. But the one thing you note is on the right-hand side is that it is true that execution time is not always perfectly represented by optimizer costs. So you can make a generalization and say that, there's a pretty good correlation between the two, but as demonstrated here, it's possible that while we're minimizing optimizer cost, we're not fully minimizing execution time, as shown by this diagram. So by taking the transfer learning approach and trying to fine-tune further, we can continue training on the cost-only model with execution time. Now this takes less than 14 hours for 4 episodes, so it does take longer than the previous cost-only model, but combining both of those, it actually is less than just running it all on execution time, right? We don't have to do as much work on execution time because the model's kind of already getting a sense of what's going on the cheaper cost estimate. But anyways, here you can see the left diagram. The episode, you can see it's effective at minimizing execution time, right? As the episodes go on, it seems like the agents figured out how to converge or decrease execution time to a certain extent. Whereas, again, if you look on the right now, this is the optimizer cost. It's just a bit disjointed, right? So here it looks like we're increasing in cost, but we weren't. We're actually getting gains on execution time. So there is a bit disconnect from the two in some scenarios, but we've shown and we believe that there's benefits here to almost bootstrapping the model based on optimizer cost and then finish training on execution time, which is what we set off to minimize to begin with. So from those results, you can see training only on cost produces a configuration that results in a total execution time of 107 seconds. Fine-tuning the model afterwards with transfer learning leads to an execution time of 93 seconds. So this fine-tuning in this scenario achieved to a 15% decrease. So it's honestly up to the end user if the extra time spent training is worth the performance gain you get. Of course, this is going to be different for every workload, almost every scenario, but it's a trade-off and it's up for the user to decide. So I'd just like to say thanks everyone for listening to my presentation. I hope that gave you a bit of insight of how the research that we do at our universities kind of can help industry, and the collaboration between industry and IBM, how we can, end up creating an interesting product. So thanks again, everyone, and hope you enjoy your time at Canadian AI 2021. Spencer Bryson, signing off.